Cube roots. The volume of a cube can be found by using the formula of volume equals length times width times height. But since a cube has all equal sides, the length equals the width, which equals the height. So the volume of a cube can be found by multiplying the length times the length times the length, or since you're multiplying the same thing 3 times, it's the length to the third. So the product of 3 equal factors is now called the cube of a number because of this relationship with the volume of a cube. And you can see we have it with this example. We have a cube that has a length of 5, a width of 5, and a height of 5. So the length, the width, and the height are all equal to 5. So we're multiplying that length 3 times. That 5 times 5 times 5, which is equal to 5 to the third, which is 125. So the volume is 125, and it's the volume of a cube, so we say that's 5, not to the third, but we can say that that's 5 cubed. So let's review more perfect cubes. Let's say we have n is our first 10 counting numbers, and then we're cubing that number. So we would have 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, and so on and so forth. That's equal to 1 times 1 times 1. Then we have 2 times 2 times 2. Then we have 3 times 3 times 3, and so on and so forth. Let's complete the first 10 perfect cubes. So if we fill in our list, we have 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed is 216, 7 cubed is 343, 8 cubed is 512, 9 cubed is 729, and 10 cubed is 1,000. And again, we found those numbers by taking the number n and cubing it. We're multiplying that number by itself 3 times. Now, if we have something cubed, we would have the inverse of cubing. So that's asking the question, what number was cubed or raised to the third power? And let's look at some examples to get the answer of 125. What number was cubed or raised to the third power to get an answer of 1? What number was cubed or raised to the third power to get an answer of 8? If we look back at our chart, we can find our answers. So because 5 cubed is equal to 125, the answer of what number was cubed or raised to the third power to get an answer of 125 is 5. Because 1 to the third equals 1, that's the number we're raising or cubing to get an answer of 1 is 1. 1 to the third, or 1 cubed, is equal to 1. And since 2 to the third, or 2 cubed, equals 8, the number that was cubed or raised to the third power to get 8 is 2. We will now explore an operation that undoes cubing a number. To remind you, cubing a number is to multiply the number by itself 3 times. So cubing 4, for example, is to multiply 4 times 4 times 4 to get 64. So 4 cubed equals 64. An inverse of cubing would have you start with the cube, 64, and then return us back to the original number 4. That operation is defined as taking the cube root. So the cube root is an inverse operation to cubing. This is the symbol for taking a cube root. It looks like the radical symbol, very similar to the square root, except we have an addition of the 3, this tiny little 3 kind of on the top sitting on the radical. So that is the cube root symbol. So given that, if we go back to our example of 4 cubed equals 64, it follows that then the cube root of 64 equals 4. Performing the operation and then the inverse operation returns us to where we started. In this case, the cube root of 64 being 4 tells us that 4 multiplied by itself 3 times equals 64. Now, cube roots don't pose some of the challenges of square roots. So here we have, for example, the idea of being careful about the square root with positive and negative answers. We don't have to worry about that with cube roots. For example, 4 cubed is equal to 64, but negative 4 cubed is equal to negative 64. The original sign of the number is preserved when cubing it, because 4 times 4 times 4 is equal to 64. When 4 is positive 4, we have a positive product. And negative 4 times negative 4 times negative 4 is equal to negative 64. We have a negative product. So we don't have to worry about principal roots or using context to find the sign of the answer. It will come when you take the cube root. You'll see it in the original problem right away. Similarly, the cube root of a variable or of variables is more straightforward as well. For example, if we take the cube root of x cubed, that would equal cube. And this is since cubing preserves the sign of the original number. We don't care if the original number is negative or not because it can equal a negative number. You can have the cube root of a negative number and it can equal a negative number. And taking the cube root also preserves the sign. So this works for all numbers, all variables, and all values of x. We also have no problem finding the cube root of negative numbers. Real cube roots of negative numbers exist, whereas their square roots do not. If you recall, taking the square root of a negative number led us to the no real root, but now if we take the cube root of a negative number, it will just be a negative root. So let's try finding different cube roots. Let's put this all together. So we have the third root of 27. That's again asking what number cubed or to the third is equal to 27. Now we have the third root of negative 8. And at first, again, if you're thinking of square roots, we would say, oh my gosh, this is not okay. We would have no real square root, but this is a cube root. So this is okay. We can find what number multiplied 3 times by itself would equal negative 8. We can have the negative on the outside of the cube root. For example, this is asking what's the negative cube root of 125. And then we can have the cube root of positive numbers as well, very similar to the first one here. The last one, we have the cube root of 216. Again, all cube roots, so we're asking what number to the third equals the number underneath the cube root. And this third example, we'll have to make our answer negative. So the first answer is 3. The cube root of 27 equals 3 because 3 cubed equals 27. The cube root of negative 8 equals negative 2 because negative 2 cubed equals negative 8. Negative cube root of 125 equals negative 5 because 5 cubed equals 125, and then the negative on the outside tells us to make our answer negative. And the cube root of 216 equals 6 because 6 cubed equals 216. So here we have a list of our positive whole number cubes. So the whole numbers in the right column are cubes of the whole numbers in the left column. The numbers in the left column are the cube roots of those in the right column. If you multiply a number in the left column by itself twice, you get the number in the right column, or including that first number if you took it, so it's a total of 3 times. For instance, let's say we looked at this row here. We have the number 9 and its cube 729, right? 9 times 9 times 9 is equal to 729. Let's say we chose this row here. We know that 4 multiplied 3 times. 4 times 4 times 4 is equal to 64. 7 times 7 times 7 is equal to 343. 1 times 1 times 1 is equal to 1. So you can take any number in the left column and multiply it by itself and then 2 more times, and then you get the number in the right column. Now here we have this list where, as you can see, the signs of the cubes of negative numbers are also negative. So here we have a list of negative numbers and their cubes are negative. And every negative cube has a negative cube root. They match. Now beyond these whole numbers, cubing any rational number results in a perfect cube as well. So here are more examples. We have the third root of 125 equals 5. Because again, by definition, 5 cubed is equal to 125. Now we have the cube root of negative 125 is negative 5 because negative 5 cubed equals negative 125. So that's a difference in signs. We have the cube root of negative 512 is equal to negative 8 because negative 8 cubed is equal to negative 512. And the cube root of 1 is equal to 1 because 1 to the third, or 1 cubed, equals 1. So notice our signs are matching up. When you cube a positive number, it equals a positive number. When you cube a negative number, it equals a negative number. So you just have to be careful of which one you're talking about and pay attention when you're taking that cube root. However, many rational numbers are not the result of cubing a number. So not all rational numbers are perfect cubes. So given a rational number, how can we determine if it is a perfect cube? Like we learned with perfect squares, for a rational number to be a perfect cube, its numerator and denominator must be perfect cubes. So here's an example. We have the cube root of 8 over 27. So we can split that up into the cube root of 8 over the cube root of 27, which is equal to 2 over 3. This example shows how to find the cube root of a fraction. And it shows that 8 over 27 is a perfect cube with 2/3, or 2 over 3, as its cube root. This is an example of a perfect cube that is not a whole number. So note that for this fraction to be a perfect cube, both its numerator and denominator needed to be perfect cubes. We had to be able to take the cube root of 8 and the cube root of 27. It wouldn't have worked if it was the cube root of 26 or the cube root of 28 or the cube root of 7 or the cube root of 10 in the numerator. It had to be perfect cubes in the numerator and denominator in order for us to do and complete this example. Any rational number consisting of a perfect cube in the numerator and denominator is itself a perfect cube. That provides an infinite number of perfect cubes between any two numbers, for instance, between just 0 and 1. And then you just put 1 in the numerator and keep putting the next highest whole number perfect cube in the denominator, since 1 is a perfect cube itself. Since the whole number perfect cubes extend to infinity, so too do the number of rational perfect cubes between 0 and 1, or between any two whole number perfect cubes.
Here's the series of rational perfect cubes with 1 in the numerator. While we stop at 1 over 1,000, there's no limit to how small these can become. And there's nothing unique about having 1 in the numerator. We could use any perfect cube in the numerator.